In this problem, a membrane-lined landfill generates a peak leachate flow of 1 CFS that must be conveyed in a full-flow HDPE circular pipe. Manning's roughness N equals 0.01 and the pipe slope is 1%. The design also requires that the flow velocity when conveying 1 CFS not exceed 5 feet per second. Which of the following nominal pipe diameters in inches is the smallest that satisfies both the flow and the velocity constraints? So in theory, this is a problem that could be on either the water resources or the environmental exam, but given that it's landfill leachate related, it's much more likely that it's going to be on the environmental exam. So we're going to use the equation from that exam's reference manual. So if you search Manning, this will bring you to Chapter 1, the Manning's equation, on page 9. And that's going to be equal to V equals K over N times the hydraulic radius to 2/3 times the slope raised to the 1/2. If we keep in mind that Q equals VA and K equals 1.486 for US units, we can further expand on this equation. So instead of solving for V, we can instead solve for Q by adding the area term into Manning's equation. This is pretty common, so you've probably already seen it before. And it's going to be Q equals K over N times the area now times the hydraulic radius raised to the 2/3 times the slope to the 1/2. Furthermore, we can identify what the minimum required cross-sectional area would be for this problem if we divide the peak leachate flow of 1 CFS by the maximum allowable velocity of 5 feet per second. And as we can see here, the minimum required area of the pipe would be 0.2 square feet. So now that we've established which form of Manning's equation we need to use, given the types of terms we have available to us, we can write these out and begin to fill them in. We can experiment to see which pipe sizes meet the criteria described above by simply plugging in the diameter of those pipes into Manning's equation. So we can see that Q equals 1.486 over Manning's N of 0.01 times the equation for area of a circular pipe, which over here we'll write down A equals pi times d squared over 4. So in the equation we can write pi times 0.5 feet squared over 4, which is what 6 over 12 is going to simplify to, times the equation for hydraulic radius, which is just going to be area over wetted perimeter. So that's going to be pi times 0.5 squared over 4 again, over the wetted perimeter equation is just pi times diameter, so at the bottom we'll do pi times 0.5 feet. And this entire fraction is going to be raised to the 2/3. And then finally, the slope of 1%, aka 1 over 100, equals 0.01 as it fits within the equation. And that's square rooted. So this is a little bit annoying to plug into your calculator, but you can simplify a little bit to make it a little bit easier. Now, assuming you do this correctly and don't mess up any terms in your calculator, you should get a flow of 0.73 cubic feet per second when the pipe diameter is 6 inches. Since this is less than our peak leachate flow of 1 CFS, there is not enough flow able to be delivered through this pipe, so we have to look at the next one on the list. So we will simply rewrite the Manning's equation again. swapping out the 6 inches for 8 inches. So Q is going to be equal again to 1.486 over our N of 0.01 times our area, which is equivalent to pi times 8 over 12 quantity squared divided by 4 times the hydraulic radius, aka the area over the wetted perimeter. So that's going to be pi times 8 over 12 squared again, quantity over 4, over pi times 8 over 12. Red is just supposed to help highlight what's changed between the equation above and this current equation. And then our slope is going to be 0.01 again. And as is before, some of our terms will cancel out. And if you can plug the rest successfully into your calculator, you should see that flow is equal to 1.52 cubic feet per second. So the 8-inch pipe can achieve a peak leachate flow greater than the amount required for our landfill, so this will pass. Now that we know it meets the flow requirement, we have to check to see if it also meets the design constraint for the velocity. Now when checking to see if the velocity is going to be less than 5 feet per second, it's important to remember that we aren't going to use the pipe's peak flow as is derived from Manning's, but instead just the value for the peak leachate flow that is actually going to be coming from the landfill. So that would be an easy mistake you could make here. But we're not going to make that mistake. Instead, we're going to write out again that V equals Q over A, plugging in our Q of 1 CFS given in the problem statement, and divided by the equation for area of the pipe, which is going to be pi times 8 over 12 quantity squared divided by 4, giving us a velocity of 2.9 feet per second. As we can see, this does satisfy the velocity constraints, so the 8-inch pipe would be acceptable for this design. So the hardest part of this problem really isn't the concepts, given that the problem statement already tells you you're going to need Manning's equation. Instead, it's just going to be manually plugging things in and keeping Manning's equation organized. Also, we got lucky by guessing that it was one of the smaller 2 pipes, so we started with 6 and then moved on to 8, whereas we could have started with 12 and worked our way down, so that's a little bit of a toss-up as well. But this problem's not very difficult. Just do your best to stay organized, and you should be able to calculate out to the right answers. And that's it.